I'll do this so I know. All right, I'll begin with a word of prayer.
Heavenly Father, we thank you for this day, and I just pray that you'd help us to understand what we do and to glorify you, Lord. In your name I pray. Amen. So I still owe you guys some discussion of Green's theory, like the Green's functions, and I'm just not there conceptually yet. I mean, I know kind of what they are, but I just don't know how to say with authority interesting things about them yet. So to buy time, I will show you guys further calculations with the method of Laplace transforms. And hopefully this time we'll actually get one we can do the whole way through. I don't know. This is the book I had, Boundary Value Problems, 4th edition by Powers. This was my book for my second course in differential equations. We have math, I think it was math 401 at NC State I took with Dr. Martin. We used this book, but I don't think we ever did Laplace transforms, but anyway, as is often the case, there's tons of stuff in the book covered in class. But so let's see. Here's an example. So this is example 1 from page 378 of that book. And the generic thing here is using Laplace transforms to solve PDEs. And the specific one we're going to look at is partial squared u partial x squared equals to partial u partial t. This is a heat equation. And we're going to look at it for 0 less than or equal to, well, he doesn't have equals. I'll limit the equals to 0 less than x less than 1. And t bigger than 0. And we're also given u of 0t is 1, and u of 1t is 1 for t greater than 0. And finally, u of x comma 0 equal to 1 plus the sine of pi x. Okay, so yeah, I suppose, so we've got, I guess technically those aren't homogeneous boundary conditions, are they? Like our homogeneous boundary conditions, I think we have to have equal to 0, right? Yeah. So these are technically inhomogeneous boundary conditions. But it seems pretty innocuous, this problem, so I have hope that it's not going to be too bad. Let's see. Okay, so what we do is we take the Laplace transform, and the Laplace transform is taken with respect to, let me see here. Here's what he says. Let me just give you a little of the theoretical backdrop, and then we'll actually apply it to this example. He defines the Laplace transform of a function of 2 variables, basically treating the x as just something that's riding along. So integral from 0 to infinity, e to the minus st, u of x comma t, dt, and that, in the notation we use for that is big U of x comma s. All right. So in the usual differential equations course, you just have u of s, right? But here we have another variable x floating about. So like, for example, he gives us an example. If you calculate the Laplace transform of e to the minus at sine of pi x, what do you get? Basically, the sine of pi x is just riding along. So you guys know what the Laplace transform is of e to the minus at. It's what? 1 over s plus a, s minus a, I forgot. S plus a. Yeah, you guys Your livelihood depends on it more than mine. Okay, it's good. Another example, he gives the Laplace transform
I believe isn't it squared?
No.
You don't have to go with the domain.
Uh-oh. When did you turn in that test?
Oh.
So your sine of x plus t.
Wait, squared. Guess what's that? Isn't it squared? I don't have the table in front of me.
If it's t,
Oh yeah, no, sorry. Okay, I was looking at the sine pi of x, but it's not dependent on d. Sorry. Okay.
No.
It's
If
been
it
a
was
long
t,
day.
if it was t times
Yeah.
e to the t, I think it's isn't it
Sorry.
e times e to t times e to the t that gives you like a
Yeah.
sort of squared. I'm about to teach Laplace transforms like next Tuesday in DiffyQ, but it's been a while. I mean, I don't.
The t.
Yeah.
Once I lecture on Laplace transforms for about 2 hours or an hour and a half or so, then I know it all again, and then I'll promptly forget it after about a month.
It's just using the table. Yeah.
Tables,
I just remember.
Well, once you derive it.
you weaklings. It's here. Sine of x.
Sorry if my comment that was incorrect.
Tables. Tables. We don't know stinking tables. Let's hear. Cosine.
Don't tell Dr. Wang.
Tables.
Put some on the exam.
Tables. I'm just kidding. I'm planning on handing out a table to them next class. But anyway, so, adding angles formula, and then basically, you guys know the Laplace transform of cosine t is s, and then the sine of x, the sine of x rides along. It's essentially a constant in this process over, s squared plus 1, and then then you got yourself a cosine x over s squared plus 1. So basically I'm just piggybacking on top of the Laplace transforms you know and love for one variable, right? I'm sorry, maybe love is too far, I don't know. But anyway. How about the Laplace transform of the partial derivative? Partial derivative with respect to x is what? So we're looking at the integral of e to the minus st, partial u, partial x, right? 0 to infinity, ddt. And so basically we just use a little calculus here, advanced calculus, unjustified as usual. Partial x of e to the minus st u dt. So using differentiation under the integral trickery, which presupposes certain conditions on u, which this book doesn't go into either. So I'm just like, yeah. Partial u, I mean there is something to prove there, but again that's kind of not the point of this course. So big partial u, partial x is what that is. So it doesn't change derivatives with respect to the untransformed variable. But in contrast, of course, I mean, the difference is if you take the Laplace transform of the time derivative, though, right, the partial u, partial t, well, that's a different story altogether, right? See, there, basically, we notice the product rule, partial t, e to the minus st times u, right, is what? It's minus s e to the minus st times u plus e to the minus st times partial u, partial t. So, if you look at that, this is exactly what we got here, right? So I can trade that for an integral 0 to infinity partial t of e to the minus st times u plus s times e to the minus st times u, right? Now, of course, the first term there is just e to the minus st times u evaluated from 0 to infinity. And then we have plus s times the integral from 0 to infinity of e to the minus st times u dt. Well, assuming that u has exponential order alpha, the infinity term vanishes here. But on the other hand, 0 gives us e to the 0 times u of 0. X is fixed, so that gives me u of x comma 0. And then this gives me plus s times big U of x comma s. Alright, so let me just make sure I'm actually in the... Did I get it? I think I got it. So, let me just record the result here. Any questions about... It's just integration by parts, the usual proof, right? You know, so many interesting things are just integration by parts. Anyway, here, u, so we got u little u of x comma 0 plus s times the big U. All right.
I vaguely remember Dr. Wang making us prove it on the test.
Oh yeah?
The integration by parts expansion of it.
Yeah, oh, that's what he was complaining about. Oh, not this semester? Different semester?
Oh yeah, it was a long time ago.
But he was just telling me something like, yeah,
Yeah, I think we did.
yeah, they anything proof, they just, so,
Yes, I done that.
horrible. Something. And so I was thinking, what does he mean proofs? And then I realized, oh, now that you say this, it makes me think that's the kind of proof he's talking about.
Well, he does induction proofs too.
Oh,
But
okay.
other than that, not.
For annihilator,
Typically.
but that's it.
Speaking of which, everybody in the class, 3334, was complaining about his test the other day.
Really.
I don't think it's that bad, but
Yeah, they shouldn't complain.
they should complain.
Maybe I. Okay, well, anyway.
They copy the homework solutions and then they get angry when they don't understand it. Sorry.
Yeah, isn't that weird? You copy the
Sorry.
homework. I mean, it's shocking that if you just copy homework solutions, you don't learn a course. It's weird. It's really weird. I don't know, it's almost like they're not really interested in the course and they're just trying to get credit towards the degree. They don't care about an education, they just care about a degree. Not our students, of course. But anyway. Sorry.
You're indoctrinating us.
So, take the Laplace transform of this thing, yeah? Now, I mean, essentially the theorem is that, I mean, more or less this theorem says that the Laplace transform and the partial derivative with respect to x commute. You know, you can like switch the order of them. Right. So if you can do it once, you can do it twice. So this up there is exactly partial squared big U partial x squared. And this guy over here, let's see, it was the Laplace transform of partial u partial t was little u of x comma 0, right? Plus s times the big U. Right. Now what is this?
That is what we define it as. 1 plus sine of pi.
Uh-huh. Okay, so this basically gives us, we can rewrite this as u prime prime equals to 1 plus the sine. I mean, with the understanding that the prime indicates an x partial derivative. There's some danger in that notation, of course, but anyway, plus s times u. Right. Now what can we do? I mean, that's an x derivative. S is appearing algebraically, right? I mean, so we really have u prime prime minus su is equal to 1 plus the sine of pi x. Right?
I mean, we can treat s here as just a constant coefficient, right?
Mm-hmm.
So
Right.
I mean, so there's going to be a homogeneous part,
Yeah.
and then we have to solve for just a particular part, which in that case, 1 plus sine of pi x. We can't.
Oh. Huh. Interesting.
Would it be correct though? Like we solve for homogeneous part, and then we solve the particular for the particular solution. Like kind of feeding in
Well,
a
I think
feeding in a
you're-
dummy function.
No, I don't. Well, it doesn't. Maybe. But there's still something else we have to do, which is we have to Laplace transform the Laplace transform the differential equation, but I also have to take the Laplace transform of the boundary conditions. These guys. We have to take the Laplace transform of those as well. The initial condition, right? This thing here. That was already worked into the transform of the equation, right? That data's already wrapped into here. So
It's gonna be 1 over s.
Yeah.
What do we put that in at though?
let's see here. So we've got d squared u
It's 6 o'clock
dx.
p.m.
We'll be quiet. We've got this, and also let's see here. Laplace transform of u of 0t, right? Is equal to the Laplace transform of 1. So this gives us u of 0. Excuse me. U of u of 0.
S.
Dang it. S, yes, I'm sorry. Eventually I'll get it. U of 0s is equal to 1 over s, right?
Equals 1.
And likewise, same for the other one, we get u of 1s is equal to 1 over s, right? So let's see here. Now we have u of 0s equal to 1 over s, and we also have u of 1s equals to 1 over s. So we have to solve this boundary value problem. But it's a single variable boundary value problem, so it's like, not too bad. Well, I don't know. It remains to be seen how bad it is. Let's try to solve this thing.
Solve for the roots of the homogeneous part.
Yeah, let's see here.
R squared minus s. Square root of s.
Sorry, his solution here is mysterious to me.
It'd be double rooted, wouldn't it? So it'd be plus or minus square root of s, right? Plus or minus square root of s, so the homogeneous part would just be constant times e to the square root of s.
I think he solved this by the method of Laplace transforms, actually. No, that can't
What?
be, because you've got this here. Well, huh. Let me think about this for a second here. So, let me rewrite it this way. We have y prime prime, right, minus s times y equals to 1 plus the sine of pi x, right? And we know that y of 0 is equal to 1 over s, right? That's a partial. I mean, we also know, by the way, that y of 1 is equal to 1 over s, right?
Well, it's almost like an initial value problem.
Yeah, if I ignore that, I've just got an initial value problem. So maybe I can find the general solution to the initial value problem
Yeah.
and then just plug in the... It doesn't seem... well... Let's try to solve it anyway, okay? Sorry, Jess, I'm not trying to ignore you. I just don't have confidence to do what you're saying. What were you saying?
Well, I mean, first solve for the homogeneous part, since we can treat s as just a constant coefficient and it's
Yeah.
linear. So we get like the root equation r squared minus s for the homogeneous part.
Mhm.
So r is just gonna be plus or minus square root of s.
Yeah.
And so that gives our homogeneous part of the equation
So
exponential to the
so I would expect to see like y equals square root of exponentials, right? Like
yeah. Constant times e to the square root of s t and
yeah, that is
negative
not
s to the
that is
square root
not
of s.
at all what the solution is given here. So
Really?
yeah. Huh.
How would that not work though?
Well,
Could it be that we get like the homogeneous part and the initial conditions just make them go to 0? Which would be why they're not evident in the solution.
maybe. Yeah, maybe that's it. I mean, what you're saying is reasonable. I should be able to solve it that way. Just when I look at their solution, I see. Well, okay, let's try it your way. So y
Now I'm worried if it's going to be incorrect.
is equal to c1, and I don't know if s is positive or what's the deal with s here? Like, what's its domain?
S always has to be greater than 0
Why?
because that's the root. The root is 0. Anytime you're dealing with it has the integral that we're doing from s is from 0 to infinity,
Okay.
which affects our root. I think, which means s has to be greater than 0.
I'll buy it. So that means that this is y prime prime minus square root of s squared, right? That's the whole corresponding homogeneous problem anyway. And so we get like c1. There's various ways to write this. I'm going to use cosh. Cosh the square root of s x, right? Plus c2 sinh the square root of s times x. That's my homogeneous solution. Pretty clearly, well, yeah, pretty clearly there's no overlap with 1 plus sinh, right? Let's see here. So y of, but I can't fit these, ignoring the particular solution either, can I? Mm-mm. So the particular solution should have the form a plus b sine pi x plus c cosine pi x, right?
Yes.
And we need yp prime prime minus s times yp. Well, that is exactly minus sa plus minus sb minus pi squared, I think. So let me think about this in my head for a second here. So if I twice differentiate this, I get out of minus pi squared. If I twice differentiate that, I get minus pi squared. So I've got like, you just rewrite them in order. So I got minus pi squared b, right, from this, and I've got a minus sb from that. And likewise, all of that's supposed to be equal to 1 plus the sine of pi x, right? So that tells me that
A is negative 1 over s.
right,
And then negative pi squared b minus sb is equal to 1.
so b times
Oh, that's not going to be hard to solve.
b times s plus pi squared equals to minus 1, right? So b is equal to minus 1 over s plus pi squared. And c is equal to 0. Right?
That's a particular.
Yeah.
Well, our particular solution is just negative 1 over s.
So I'll go back up here and I'll write it out. We have this plus, or this minus 1 over s plus pi squared minus 1 over s, right? There's our general solution.
Well, don't forget the sine by x in the...
Oh, yeah, thank you. Sine pi x, right? That's whack. You just got like a... Oh, I'm a sign off, right? I'm a sign off here. Look. This is what? Age-old mistake.
Oh, it's negative since it's...
Yeah, very popular mistake. I made it over here. So there's a minus, lower bound, minus, which then puts a minus,
So it's going to be plus. So plus 1 plus.
minus. Sorry, I'm getting confused out of this. So that just makes this a plus. A plus, basically. Yeah. So in the end, our oddly negative solution becomes positive in the particular part. That was my mistake. Okay, so we got that. Now, I'm going to erase this because I want to then focus on the boundary conditions. You know, already I see part of the sort of, it seems artificial to me. When I study boundary value problems, so often the case, if you just pick a pair of random boundary values, there's really no guarantee you're going to find solutions to a fixed differential equation which permit, those boundary values. So the fact that we can fit these in this set of solutions, to me, is rather, seems to me to be artificial, but maybe I don't appreciate something else about this, I don't know.
Are we looking like we're on track for the form of solution yet?
Oh, I think we're fine. I think your method's going to work. I think we're going to find a way to their answer. I think what you said about C1 and C2 being 0 is going to be correct.
I know you like Cauchy cinch, but can we change it to exponents for ease of computation for initial values?
What do you mean? That's why I use Cauchy cinch.
Oh, really? I was just like...
That's exactly why I use Cauchy cinch, though. Because y of 0 is c1. That's 0.
Oh, yeah, well, yeah. Your goodness making me feel stupid again.
It's just funny that you say that because that's exactly why I
yeah.
go to the trouble of using Gaussian edge.
Oops.
But anyway, it's fine.
Like I said, long day.
On the other hand, yeah, y of
Sorry, that's my excuse today.
y of y of 1. Now, yeah. Now this one's going to be less fun. Well, this R's already gone, so we just got C2. Sinh of square root of s, right? Plus the sine. Oh, sine of pi. Sweet. So that's equal to what? 1 over s, right? So these cancel, that's 0. So we get C2.
Because of 0.
But the sinh is never 0 unless you input 0.
Mm-hmm. So C2 has to be 0.
You must embrace the Gaussian and the sinh. They're your friends. They actually save you work if you get to know them. See here. There you go. Anyway, so your conjecture was correct, Mr. Gregory. So the in summary, we find that u. Okay, so backtracking over to here, solution to this is that u of x comma s is equal to sine of pi x over s squared plus 1 plus 1 over s. Right?
And then we can find u of ts, right?
So we
U of
took
C.
we took the Laplace transform, right? To get over to this frequency domain. And now we take the inverse Laplace transform to get back. So that will give us u of xt equals to the inverse Laplace transform with respect to t, right? Sine pi x over s squared plus 1 plus 1 over s. Now 1 over s, you know what that is. This is sine t, right?
Yeah.
Sine t sine pi x. And that guy,
1.
1?
1, yeah. It's exponential.
Oh, yeah.
So it's just
Yeah, you're right. I just derived that last differential equations class. Shame on me. So anyway, that is literally the last thing I did last differential equations class is derive this. So it is truly sad that I did not know right off the top of my head. But anyway, there it is.
beautiful.
It is very beautiful, right? We just solved the partial differential equation using the method of Laplace transforms to convert it to an ODE.
That's really cool.
But the thing is, you have to convert also the. It'd be cooler if we could see the solution. You do have to Laplace transform the boundary conditions as well, don't we? So.
The only reason we held like x fixed was because the boundary conditions correct.
Yeah.
Like we're given in forms of like for all t, just fixed x.
Hey, but this is nice, right? We solved a non-homogeneous boundary condition problem, right? Also. So, I mean, there's some simple substitution you can make. Like this kind of one especially, what would you make? You just make a substitution, let v equal to u minus 1. If you let v equal to u minus 1, then in v you have v of 0t, 0, v of 1t, 0. That gives you homogeneous boundary conditions. Then you can use the usual Fourier stuff to take care of that. And the solution to that in the world of the Fourier, it's a Fourier sine series, and it has one. You'd get this as your solution for v, sine t sine pi x, and then to get back to u, you have to add 1. This problem is actually pretty easy if you go back and use the other techniques we've done. But still, I mean, come on, it's a cool example. Definitely beats the pants off what I tried last time, which required an unhealthy portion of complex analysis we don't currently have ownership of. All right, so not that it's outside your grasp, it just would take time.
Also laughing at how you accidentally called it frequency domain once.
Oh, well, that's what it's called, right?
Yeah.
That's your, if I say that, it makes it more legitimate, right? I've learned that if you're talking to engineers, you should use some of their jargon.
We're not engineers. Everybody
Well-
here is a math major.
Oh, okay, good. Yes. What am I saying? But you're talking about taking this test, and since I don't know if he tested the Laplace transforms as a take-home, I can only assume that that was an engineering activity. And as such,
Yeah.
some amount of engineering jargon might ring true to your ears.
Actually, Dr. Bay, he doesn't call it frequency domain. He calls it S domain.
Yeah.
Okay.
Melendi calls it all frequency domain.
Ah,
But Bay's a lot
actually
more.
works with
Bay
frequency.
appreciates theoretical math a lot, like
He does.
and abstractions and stuff. So.
And he
Good.
does frequency.
all right. Let's try another.
Mm.
Example 2.
Stop it, Cooper.
It worked.
Here we're looking at partial squared u, partial x squared, equal to partial squared u, partial t squared. So this is a wave equation. 0 less than x less than 1, t greater than 0. And he's going to give us that u of 0t equals to 0, and u of 1t equals to 0. For t greater than 0, there's your boundary conditions. And we need two initial conditions, right? U of x comma 0, sine pi x. These examples are embarrassingly easy compared to last time. Partial u, partial t, initial velocity, uxt, x0 is minus sine pi x. See, I shouldn't even show you guys the solution to this so I can give it to you as a problem. Oh, well, too late. All right. Oh man, I've erased all my favorite my. I think we know now what to do, right? So we take the Laplace transform of the PDE. That gives us big U. I'll use the partial derivative notation. Partial squared big U partial x squared equals to what? How do you take the Laplace transform in the time domain? I'm trying to remember how's it go. Is it minuses on everything, or is it just minus? I mean, it's
Minuses on everything but the first term.
so it's like s squared big U minus s times u partial t of x comma 0, right? And then minus u of x comma 0, right? Taking the time Laplace transform. And so that is exactly, that gives us, of course, u prime prime minus s squared u equal to, well, that was nice of them. Look at that. So he made it s sine of pi x minus the sine of pi x, right? Disagree? So, Jess has given me courage just to solve these things outright. Oh, wait a minute. One more thing. And u of 0s is 0, and u of 1s is 0, right? Say taking the Laplace transform of the boundary conditions, Laplace transform of 0, 0. Laplace transform is a linear transformation, so good to know. So now we face a innocuous, harmless little boundary value problem, one variable, and so we will get us.
Dang it, Cooper.
It's so good.
What's that?
It's like use the annihilator method.
Yes, C1.
It's so fun.
But I don't need to because I understand C1.
It's true.
C1 cosh s x plus C2 sinh sx. Sorry, Jess.
No, I admit my fault.
And then the particular solution, whatever that is. Oh, why don't I be a civilized human being and write this as s minus 1 times the sine of pi x? Duh. So let me hear some particular work. So if up is equal to a sine pi x plus b cosine pi x, then of course up prime prime is minus pi squared up. So up prime prime minus s squared up is going to give me minus pi squared minus s squared up equal to s minus 1 times sine pi x. That implies b is equal to 0 and a is equal to, by my count, well, I mean, forget the, I mean, actually once I do that, do you need to equate coefficients anymore? You really shouldn't need to equate coefficients once you come to that equation. We should just be like, okay, so check it out, up is equal to s minus 1 times the sine of pi x, right? Divided by, minus s squared minus pi squared. Or, to be more civilized, the particular solution is 1 minus s times sine pi x over s squared plus pi squared. Oh, sorry, this is u of x s, right? Technically. Now we should apply our boundary values for the big U. What does that give us? U of 0s equals to what? C1? Oh, that's 0. So it's gone. So C1 equal to 0. U of 1s. Oh, see, this is really stupid. So 0 and 1 both make this particular solution 0. So the fact that the particular solution is 0 at both of the boundary values means that this thing has to be 0. But anyway, so C2 is the other thing, C2 sinh of s equal to 0, which of course says that C2 is equal to 0. So therefore, U of xs is equal to 1 over s squared plus pi squared minus s over s squared plus pi squared times the sine of pi x. So taking the inverse Laplace transform with respect to time, this gives us u of xt equals to 1 over pi sine of pi t minus the cosine of pi t times the sine of pi x course, we need the 1 over pi because the inverse, the sign has a pi upstairs. When you've got a pi squared is the argument, the multiplier of the argument of the sign. So usually, usual pi over pi in your imagination. Oh, I'm an idiot. Well, no more than usual. So I forgot that this is multiplying. So, there we go. Yay, we just solved the wave equation without the Fourier technique.
Does this work for like? It seems like it's a universal thing.
So kind of like
No.
kind of like those aliens in that movie once they discover, you know, the joy of the human endorphin as a drug. They want more, you know.
Cooper,
Sorry, it's a somewhat obscure
read
reference.
this book. Oh.
Sorry, this channel has been replaying various. They've been very Dolph Lundgren this week. So Dolph Lundgren is in this movie about intergalactic drug dealers because it's the 1980s. So it's like the war on drugs, you know, it's big. So you can make an action movie. Why not make it about drugs too, right? What's more evil in the mid 1980s than drugs? Really nothing. Russia, I mean, there's glasnost at this point. I mean, no, not really. I mean, we're getting there. But so I mean, drugs were evil, like the most evil. So alien drug dealers shooting heroin into people in order to, just as they're dying, they get this rush and then they extract it and then they make some drug from it. So there's like these 8-foot tall aliens that Dolph Lundgren runs around chasing, and they've got these alien guns that make everything blow up but no one can get hurt. It's pretty fantastic. You've never seen this movie?
No. What is it called?
Oh man.
What is it called?
I don't remember. But you'll know it when you see it.
Remember in Signs, the kid was like...
I mean, it's very well known in terms of memorable lyric. Like at the beginning, I think the alien says, "I come in peace," and then finally, when like Dolph Lundgren kills him at the end, he's like, "And you go in pieces." It's very. It's. It was like one of like the movies that was discussed when I was like 12. Like we were like, "This movie's awesome." You know, we would watch it, of course, on TBS. Back anyway, but maybe I was 14. I don't know. But anyway. Ooh.
Immediately want more problems that are like this, but even harder. That's what Laplace is great at.
Well, there is a harder. Oh wow. So you guys want me to get? I have a harder problem here. I can give you as a homework problem.
Wait. Before you assign it, can you tell Cooper that he can't do the annihilator method?
No, that's so easy. But why, it's so easy. Why is it bad?
It's not bad. It just doesn't solve it for you. It just tells you the form of the particular solution. It doesn't tell you the A and the B.
It's true.
Yeah. You can do it really fast though.
I can do it even faster. I just write down the form.
Admit it, Cooper.
I just say it because
Admit
my
it.
entire 334 final, I used the annihilator method for the entire test.
I see. Pretty much.
Admit it, Cooper.
It's still my favorite.
No.
All right. There is a. I'm gonna save as example 3 and give it to you guys as a homework problem, so you have the joy of doing something a little bit harder.
That's what you get for ignoring writing this and writing the differential operators instead.
Well,
I'm sorry.
maybe
What page is it on?
Maybe I should do it. Oh, you guys don't have this book.
Oh yeah, it's not.
Sorry.
can't. He said you can't.
Eh. Well, anyway, I think I will. I think that's enough of those in here for now. I will try not to use up all of the cool examples in here. So I think there's some good homework problems that I'll give you out of here, since I have had trouble finding ones that are not horrible. Okay, so let's look at the next. Now there's two main transforms that are used to solve PDEs in this kind of flavor. The other is the Fourier transformation. The Fourier transformation also has significant theoretical meaning in quantum mechanics. So maybe I should look at that actually.
Is it because everything's like the sum of waves?
Yeah, let me see if I can't find that in Griffiths to look at, because I think I'll need longer to develop the mathematics of the Fourier transformation. So I don't think I have time for that, but maybe I've got enough time to talk about what does the Fourier transformation look like in physics, at least a little bit.
Is it kind of the same process as solving with the Laplace? Like you transform it and then you do a bunch of stuff and you untransform it?
Yep.
Yeah.
It's another integral transform, so it is something like that. Let's see if I can find it introduced in here. Come on. So page 46 apparently. I still haven't had a chance to look at the one you guys were stuck on. Have you guys made further progress?
Not yet.
Yeah. Alright.
I did finish the third problem incorrectly, I think.
Hopefully this weekend I'll have more time to look at it too. So
Yeah.
Okay. That works for me. So here's the story.
yeah.
We've talked about the wave function. Psi, which is a function of x and t, right? Now, so that's a solution to the possibly time-dependent Schrodinger equation, right? And what he says is this you can write as the integral. Well, excuse me. He says you can write this as 1 over the square root of 2 pi, which is a convention. The integral from minus infinity to infinity. All right. Phi of k, e to the I, kx minus h bar minus h bar k squared t divided by 2m dk. Says this is basically a continuous. It's a continuous sum over the variable k. 1 over square root 2 pi is for convenience. Let's see here. For wait, let's see here. So in a generic quantum problem, we are given the initial wave function psi of x0, and we are to find psi of xt. For a free particle, the solution has the form like that. The only remaining question is how to determine phi of k as to fit the initial wave function. Okay, so basically he says given the initial wave function psi of x0, how to select phi of k to fit it. once you fit that one time, then this integral will produce the wave function at other times, basically. Green's function. Never mind. So here's what he says. Plancherel's, which I'm sure I'm mispronouncing, theorem. He says is f of x is equal to 1 over the square root of 2 pi. We haven't, we're eventually going to state the Fourier transform here, eventually. We're getting there. This is just giving you some motivation for why it matters to physics, okay? Although I don't think it's clear yet. Integral from infinity to infinity, big F of k, e to the ikx, alright, dk, right, f of x is equal to that, if and only if f of k is equal to 1 over the square root of 2 pi, the integral from minus infinity to infinity of f of x e to the minus ikx dx. Kind of a beautiful symmetry in those equations, isn't there? So big F of k is called the Fourier transform of f of x. And on the same token, little f of x is called the inverse Fourier transform of big F of k. The difference, you notice, is in the sign of the exponent. Ikx minus ikx, right? Let's see here. How could we foolishly try this out? What if we plug one of these into the other? Would it make any sense? Let's try something different. What if I...
That just give us something stupid like f of k equals f of k or something?
I don't know. So,
I don't do that.
let's see here. So to find, anyway, by the way, the answer to this question is the following: phi of k. What you do is you do 1 over the square root of 2 pi, the integral minus infinity to infinity of psi of the initial wave function, psi of x0, e to the minus ikx dx. And if you can calculate that integral, that will give you the phi of k. Now, there is more to say than just that. This isn't the part I wanted either. I mean, this is not bad, but there's a connection with momentum, I thought. Yeah, later on page 107 in my book, we learn the following connection between the, zooming the wrong way. We learn the following as well.